Classical mechanics as the study of, so this is classical mechanics, and this is a study of motion of body. So it's a study of motion of body or system of bodies. System of bodies moving under the influence of external force. So this is all about the motion of body, and this classical dynamics or classical mechanics deals with the motion of heavy particles, that means which has mass, and classical particles. Basically we can say that this as classical particle. There are different laws which governs the motion of this body. So some laws that determines the motion of the particle which is moving under some force. First one is the law of inertia. Which says that body is continuously in a state of rest or uniform motion. So it is in state of rest or or uniform motion. Unless it is compelled by external force. By external force. So that's the first law, that is law of inertia, which says that the body is in state of rest or uniform motion unless it is compelled by external force. So coming to the second law, that is the equation of motion. Force or motion. It says that the force is equal to ma. This is actually the momentum, change in momentum, that is mv minus mu by t, or that's equal to m times v minus u by t, and this v minus u by t is nothing but the acceleration a. So a is equal to v minus u by t, and what is this m? M is the mass. Okay, so or you can write dv by dt, change in velocity. So we can write the force F is equal to m dv by dt, or rate of change of momentum p. So F is equal to dp by dt. So what does the second law says? The rate of change of momentum is equal to external force. So here you can write as a star, rate of change of momentum equal to force. Coming to the third law, it's third law, or this law is also called the law of mutual interaction. Law of mutual interaction. So that's nothing but F12 is equal to minus F21. So this is force on the first body due to second body is equal to minus of force on the second body due to first body. Okay, so and this is also called a law of action and reaction. So that's it. For a classical system, so we have a classical system, and to define this classical system we need coordinates. A coordinate system, space coordinates, space and time coordinates, which acts as the reference frame to understand the motion of the particle, to understand the motion of particle. Now here the space is homogeneous, which means the it holds the law of conservation of linear momentum. So this homogeneity implies it holds law of conservation of momentum. And towards the space is also isotropic, which means it obeys the law of conservation of angular momentum. Here we have linear momentum. And here we have time is homogeneous. And this says that the total energy is conserved. So this is law of conservation of energy. So in the first place, conservation of linear momentum means force is equal to 0, and law of conservation of angular momentum, torque tau is equal to 0. And here when you consider the time homogeneity, it says that law of conservation of total energy and the potential V as a function of Q, that means only position. It's a V is a function of only position. So just write F is equal to ma, that's equal to m dv by dt, and this also we can write it as m dv by dx into dx by dt, and m dv by dx and dx by dt. And what is this? Dx by dt is nothing but the velocity, so we can write that is also equal to m v dv by dx, and that means we have acceleration a. Now from this equation f is equal to ma, we can compare f is equal to ma with this equation as well as this equation. You get acceleration a, you have one is dv by dt, rate of change of momentum, velocity, as well as a is equal to v dv by dx, v dv by dx. So if your velocity is a function of time, you can use the first equation. If the velocity is a function of position, you can use the second equation. Here we are discussing the types of forces. First, starting with the constant force. Example, force is equal to mg. This is gravitational force, mg. So this is an example of constant force, which second is position dependent force. Position dependent force. So the example is F is equal to minus kx spring force, okay, where k is spring constant. If you are considering the spring. Now velocity dependent force. That means force is equal to some function of velocity, like air resistance force, that is F is equal to minus kv. Fourth is time dependent force. Example, F is equal to Q, which is the charge, E naught is the electric field, and cos omega t. So it's an example for time dependent force. So, and let us try to understand the position dependent force. Position dependent force. So F of x, that's the force, is the function of x, and let us understand that is equal to ma, that is mass into acceleration. So we can write F of x is equal to m dv by dt, or we can also write it as m v dv by dx Now since it is a position dependent force, we will write force as mv dv by dx. So f of x into dx is equal to mv dv, just rearranging the variables, and this integral f of x into dx, f dx is nothing but the work done is equal to m dv. So this work done is equal to m v square by 2, and putting the limits of v, we can write let this be u, that is the initial velocity, and v be the final velocity. So the work done is m v square by 2 minus mu square by 2. Now mv square by 2, that's nothing but the kinetic energy, which is the final kinetic energy, minus mu square by 2 is nothing but the initial kinetic energy, which gives us the work done. So work done is nothing but the change in kinetic energy. And moreover, F is equal to minus del V, gradient of the potential energy. So that's we can write, since if we consider along single direction, you can write minus d by dx of V, where V is the potential. Yeah, and so f of x dx is equal to minus dv. So this is from this equation, and integral f of x dx equal to minus dv integral. Now let us understand the initial potential vi, and this is the final potential vf. So this also gives you work done, that's equal to minus of vf minus vi. So but that's equal to vi minus vf. So work done. So work done is equal to initial potential minus the final potential energy. Okay, so comparing these two equations, you have equation 1 here and equation 2 over here. Both are work done, so we can write kf minus ki equal to vi minus vf, bringing the similar terms, the initial terms together, that is ki plus vi is equal to kf plus vf. So total energy is conserved, so ei equal to ef, initial energy is equal to final energy. Here we have a question, f of x is equal to f naught e to the power minus cx. So find the velocity with respect to x. Find velocity with respect to x, and the initial condition given are at x equal to 0, v equal to 0. So in the initial stage the velocity is 0. So with f is equal to ma, will begin. So that's equal to f of x and that is equal to, since we have to find velocity with respect to x, so v as a function of x, we use the formula mv dv by dx. So f dx is equal to, or integral f dx is equal to integral mv dv. So here we have half mv square, and since the initial condition at x equal to 0, v is equal to 0, we need not put the initial condition, so this is 0 to v, and the position, it is from 0 to x. So this we can write it as half mv squared is equal to integral from 0 to x f of x dx. And now let us write down what is f of x, that is the substitution for f of x here. That's it. Integral from 0 to x, f of x is f naught e to the power minus cx dx. So here we have f naught. Now the integral e to the power minus cx is by minus c, and the integral is from 0 to x. Now here we will continue. So f naught, so minus f naught e to the power minus cx by c from 0 to x. Since we have the minus sign, we will go with the lower limit first, so that's equal to f naught by c into e to the power 0 is 1 minus e to the power minus cx. So in the end we have at x equal to 0, v is equal to 0. So half mv square is equal to f naught by c into 1 minus e to the power minus cx. So we can write, bring this half m to the right side, so we become v square is equal to f naught by c, or 2f naught by mc into 1 minus e to the power minus cx. And now you can put the initial condition here. Bringing this initial condition. At x equal to 0, v equal to 0. So put x equal to 0 here. So e to the power minus x is 0. So v is equal to, we are almost getting this 0 values, because 1 minus 1 gives you 0. You have the function f of t equal to f naught cos omega t. and the initial condition is given that at t equal to 0 v is equal to v naught. We are asked to find out the velocity v. So here f of t is equal to m dv by dt. Okay, so now integral f of t by m, and this is dt. We will write it as from 0 to t is equal to dv from the initial condition, that is v naught to v. Now that's equal to f naught cos omega t divided by m integral is equal to v. Now we have v naught to v. This integral is equal to f naught minus it's plus sine omega t by, so omega t, you have omega here, so m omega is equal to, we'll put the upper limit first, v minus v naught. So v is equal to v naught plus f naught by m omega into sine omega t. So this is velocity v in terms of t, so this will be equal to v of t. Velocity dependent function. Or its velocity dependent force. So f is written as f of v, which means the function f, that is the force, depends on the velocity. So in general we can write f is equal to ma, where a is the acceleration and m is the mass of the body. We can write f of v is equal to m dv by dt, and now we have f of v, so that's equal to dv by f of v is equal to dv by f of v equal to m dt. So this integral will be like this, and this is the equation from where you can find the velocity and the function t as a function of t. Now one quantity or one formula that you can remember: integral f dash of x by f of x is equal to log f of x. Question here: consider a block of mass m moving horizontally under a resistance force F is equal to kV minus kV. Now find V as a function of T. Now, according to the question, here we have a block of mass m moving horizontally, and as it moves horizontally there is a backward force which is equal to k times v. This minus sign indicated is in the opposite direction. That means opposite direction with respect to the velocity of the block. So there is a resistive force, and we know F is equal to m times A and minus kV, that is the force, that's equal to m dV by dt. So F is the resistive force, and let us bring the terms, similar terms together. So it gives us dt k dt by m k dt by m with a minus sign is equal to dv by v, and this is integral, and this is from v naught to v. Now this is the initial velocity is v naught, and when it reaches some, or after traversing some distance, some time t, it will have the velocity v, and this is from 0 to t. Okay, so now this is log v, and that's from v naught to v, and on the left side when you integrate it becomes minus kt by m, and this one if you integrate it becomes log v minus log v naught, and that's equal to log a minus log b is log of a by b. So v by v naught equal to minus kt by m. Now we have e to the power minus kt by m, just making it exponential, equal to e to the power log v by v naught. Now e to the power log gets cancelled, so it becomes v by v naught equal to e to the power minus kt by m, and v is equal to v naught e to the power minus kt by m. So this is the velocity in terms of t. It's exponentially decreasing velocity. Now we are going to learn a concept called free body diagram. Now through this free body diagram we can understand the direction of force as well as the velocity. Okay, now consider a freely falling body, under gravity. Now we also make it that the body is falling under in a viscous medium, so under gravity in a viscous medium, so that the medium is offering some kind of resistance to this falling body. So when the mass body with the mass m falls down with the gravitational force Fg is equal to m times g, and there is a resistance force or resistive force against the motion of this mass. That means the velocity of the body is in the downward direction and the resistive force is in the upward direction, and that is given as k times v. Now, since velocity in the downward direction and the resistance force is in the opposite direction, we will put a negative sign indicating that it is against the velocity of the body. So F is equal to minus k times v. So this is resistance force Fr. Now we can say that the net force which is equal to F net, that's equal to mg, that is the downward force which is larger, minus kV, that is the resistance force. Okay. So that we can write it as m dv by dt. So this is the free body diagram, and this is the net force that we have understood, taken from the free body diagram. So F net is equal to mg, which is downward, which is considered positive because it is in the same direction as that of the velocity of the body, and kV, which is the resistive force Fr, which is against the force, that's why it is minus q. Now similar question we will take what if happens the body is projected upward. So there is a mass m which is projected upward, so the velocity is in the upward direction, and here we have downward force which is F is equal to Fg, which is equal to mg, and there is a resistance force which will be always against the velocity. So this is Fr, which is equal to kV, k times the velocity. So now let us write down the net force. F net is equal to Fg, which is the gravitational force, plus Fr, which is the resistive force. Now we can write Fg. How about Fg? Whether Fg is positive or negative. Velocity is in the upward direction and Fg is in the downward direction, which means Fg is minus, and Fr, now look at this, Fr is also in the downward direction, which is against the velocity. So again Fr is also negative, so it becomes Fr. So F net is equal to minus Fg, so that is minus mg minus kV. So this is the net force, and this is how we can write the force from the net force from the free body diagram. Few questions from this area. That's question number 1. Consider a body of mass m falling under gravity in a viscous medium with resistance force F is equal to minus kV. Find velocity of the body with respect to t. Find velocity of the body with respect to t. Question 2. A body is falling, body of mass m is falling freely from rest at a height h under the gravity. If the air resistance is minus kV squared, find the kinetic energy of the body with which it hits the ground. For the first question, velocity is the answers. The first one, V is equal to mg by k into 1 minus e to the power minus kt by m. For the second, the kinetic energy is equal to half m squared by k times g into 1 minus e to the power minus 2kh by m.